Welcome to the course on power quality. So, we will discuss today this control of shunt active power filter. Coming to the control algorithms of this shunt active power filter, we classify these control algorithm into two categories. The one category is time domain control algorithm, which like consists of unit template based algorithm or PI controller based algorithm, and another power balance theory based control algorithm, then ICAS phi algorithm, current synchronous detection algorithm, and instance reactive power theory, also known PQ theory or alpha beta theory, then synchronous reference frame theory, also known as a DQ theory, and instance symmetrical component theory, then single phase PQ theory, single phase DQ theory, and neural network theory. The simplest one is like a withdraw derived least mean square based error line algorithm, and enhance PLL based control algorithm, and conductance based control algorithm, then adaptive detecting algorithm, also known adaptive interference cancelling algorithm, and many more. So, there are plenty of algorithms which are reported for this shunt active power filter, and there is another type of algorithm which are used for this shunt active filter is the frequency domain control algorithm, like Fourier series theory, discrete Fourier transform theory, then fast Fourier transform theory, then recursive discrete Fourier transform theory, kernel filter based control algorithm, wavelet transformation based theory, then Stockwell transformation based theory, and empirical decomposition transformation theory, then Hilbert-Huang transform theory, and many more in frequency domain algorithm also. So, we like to discuss of course couple of them, we can't discuss all of them, we discussed many of them already earlier in DStatCom, but here we like to discuss only a couple of, just to give you an idea how they are like. So, the starting from DStatCom theory is made flexible, it can be modified for power factor correction or voltage regulation, zero voltage regulation through reactive power compensation with load balancing and harmonic elimination. So, it can be, you can think about like you can have a two, either voltage regulation, zero voltage regulation means you are maintaining the same voltage across the load what it could have been on the source side. So, you are compensating virtually for the by reactive power the drop in source impedance. Like this control algorithm can be used for direct current control of voltage source converter current, or it can be for reference current of typically of your filter current like However, here we have gone through an indirect current control of supply current or grid current. It preferred to obtain PWM switching signal for the devices used in current control voltage source converter working as a shunt active filter, and the indirect current control of shunt active filter offers the advantage of fast control, reduced burden on the processor, the DSP for the implementation, and inherent elimination of sharp notches in the current like The unit template or PI controller based control algorithm is simple control algorithm for active compensating devices such as shunt active filter. The control algorithm inherently provides a self supporting DC bus used for shunt active power filter, and the three phase reference grid current are derived using a sense AC voltage, DC bus voltage of the shunt active filter as a feedback signal. So, the two PI controller, one to regulate the DC bus of voltage source converter used as a shunt active filter, and other to regulate the amplitude of PC voltage are used to estimate the amplitude of in phase and quadrature component of reference supply current. These are typically the block diagram that we have a DC link voltage controller, we have a DC voltage reference which we already discussed in case of design, that how much it should be there for a particular AC voltage system, and then we are taking DC link voltage as feedback. But this DC link voltage, certainly because of nature of the system, you will have a certainly ripple on that. I mean either it will have a sixth harmonic ripple, or it can be like a second harmonic ripple if you have any unbalance in the current or voltage or both. So, certainly we use two low pass filters, so that to get a only DC component of it, which we have to regulate the DC voltage, and then we use the proportional integral controller. You can use any closed loop, other closed loop controller also, but this was the, we consider the simplest controller which can make steady state error 0. Then of course, from the typically from source voltage, I mean we are deriving the template, and in that case source voltage is also, if it is distorted or it is unbalanced. Of course, in 3-wire system we only sense the 2 line voltage, and we pass them through band pass filter, then convert to 3-phase voltages, and from 3-phase voltage we calculate the amplitude from the positive sequence voltage virtually. We calculate the amplitude and then we calculate the template. This template are multiplied with the amplitude of this current, and this current we call it the grid current or supply current, which along with the sense grid current we do the indirect current control for the voltage source converter operating as a shunt active power filter. And these are of course the expression for that. So, we sense the 2 line voltage which I was mentioning, and from this matrix we calculate the 3-phase voltages, and from 4 3-phase voltages now we calculate the amplitude of them. Then from this we calculate the template for all 3-phase instantaneous voltage divided by this amplitude, and then we have of course you can call it the DC link voltage error, and then PI controller on DC link. This output of this PI controller we consider the amplitude of supply current, which we multiplied with the template, and we get the 3-phase grid reference current. So, we sense the grid reference current and put the current controller, either hysteresis current controller or a PWM current controller or on-off current controller. There are plenty of current controller which are used on these current errors like also. So, this is typically the block for 0 voltage regulation. So, along with the typically of active component which DC link voltage, we have a reactive component also, because we have here now the voltage controller on the amplitude of the voltage, which give the amplitude of reactive component which will flow into the grid, and we get now not only the phase template from the voltage, but we get the quadrature template which are 90 degree ahead or 90 degree leading than the phase template. We multiply it and we get the quadrature component, we have a phase component, and we get the total source current. So, taking a feedback of source current, we give the gating signal to the typically for shunt active filter like and this is typically the phasor diagram how this voltage can be controlled by putting the little extra in the case of, or you can have like at substation. So, where you are regulating corresponding to that. So, without shunt active filter and with 0 voltage regulation, how we are regulating. So, virtually you have to inject a reactive current to regulate, and now power factor have to be leading, because your source current should lead than the typically your terminal your PCC voltage, otherwise it will not be able to give you typically 0 voltage regulation like. So, well, in this case also we can estimate the even a typically quadrature unit template also. So, we get the first from 2 line voltage, we get the phase voltage, then we get the amplitude, then we get the in phase template, then we get a quadrature template which are 90 degree from the template of the phase, and then we have a estimation of direct component from DC link voltage controller, and then we have a direct typically phase component, all 3 instantaneous phase component, then we have a quadrature component from the PCC voltage regulator on the amplitude of PCC voltage and PI controller. This we consider the amplitude of quadrature current which are at 90 degree reading than the your phase voltage, and then these are the instantaneous value of them, and the summing both phase component and your quadrature component we get the 3-phase grid current, and taking a sense grid current we put virtually the indirect current control for the your shunt active power filter. And this is typically another control algorithm which we call it instantaneous reactive power theory, which is alpha beta theory. Here also we have a DC link voltage controller, same way as we discussed earlier. We have a reference DC link voltage, we have a feedback voltage with the low pass filter. So, that DC component is there, and we put a DC link voltage controller for the we call it P loss. Similarly, we take a AC voltage controller in the same way with we take a feedback with the LPF, and we have AC voltage control. So, this we call it reactive power to be generated by the voltage source converter, and this from sensing the voltage and current load current we calculate the power, active power, reactive power, and this is you can call it, it has a AC and DC component. So, using a low pass filter we get the DC component. So, that we add it because this is the load active power as well as the loss in the your shunt active filter is coming from the grid. So, that is total active power flowing from the grid towards the system, and of course, for the grid reactive power. So, this is the total reactive power generated by shunt active filter minus the load reactive power, that is the reactive power. Of course, fundamental reactive power have to flow into the grid. So, taking this P and Q by taking this inverse transformation from P and Q we get the I alpha I beta, and we convert this I alpha I beta by inverse Clark transformation for 3-phase current, grid current, reference grid current, and then we have a typically sense grid current, and we have a current controller for getting the yours typically voltage source converter devices like and typically this is typically like a expression for. So, we are having a from line voltage phase voltage, and then we are having we are converting this phase voltage into alpha beta component and load current also alpha beta component. Then we are calculating the instantaneous power which consists of DC component, AC component for reactive and active, and by using a low pass filter we get only the DC component which are for the typically for the supply, and then we get the total power coming from the grid, that is the loss in the your filter plus the load power. However, the power reactive power to be generated by shunt active filter minus the load reactive power to be given locally, only a small reactive power flows into the grid for voltage regulation. So, these are the two power, and by taking these are the how we get the loss component by maintaining the DC link voltage of the your active filter, and this is reactive power to be generated by your again by active filter for voltage regulation. And then from this P and Q we calculate directly from this transformation the source grid current, reference source grid current, and along with the your grid current we do the indirect current control for the your typically shunt active power filter. So, this is another control algorithm which called synchronous reference frequency theory, very extensively used. We have a reference DC link voltage and we have a feedback DC link voltage with the low pass filter, and pass on the your through PI controller. Output of PI controller we call it the is a current signal corresponding to the loss in the your shunt active filter. Then we have a load current, and on the voltage PLL we apply to typically like a transformer DQ transformation, path transformation. We get the your these two currents virtually, but they have a AC and DC component. DC component corresponding to fundamental, so we pass on through you can call it low pass filter. So, we add this is also active component which have to be for load. So, adding this is the total active component, or you can call it active power component coming from the grid, and the reactive component which your by voltage regulator have to be supplied by shunt active filter. We supply locally this for the typically for the load, so that we subtract here. So, in the grid only this small amount of reactive power flows for voltage regulation. Again this ID IQ we transform back to 3-phase current, and these are the 3-phase reference grid current. So, along with the you can call it the sense grid current, we have a current controller to get the getting signal of this typically for the PWM control for voltage source converter operating as a shunt active filter. So, these are the typical expression. We are converting load current into DQ current, and then typically here the theta is used which we got from PLL, and this is typically you can call it, it has a DC component, AC component. A DC component is corresponding to fundamental active current, similarly for reactive current for fundamental and the ripple, and then we have the DQ component of the load current are passed through the low pass filter to extract ILD and IQ, and the amplitude of direct axis and quadrature axis of reference current are calculated by loss plus the load active component, that is the total active component. And for reactive component we of course what the shunt filter have to generate minus the load which is supplying locally, that goes to the grid, and zero sequence in the grid will be 0. And then loss component, that is the loss component which is used here, it is calculated by PI controller. Similarly, reactive component also use PI controller on the PCC peak voltage, like that is another PI controller to regulate the voltage at PCC. And then we calculate from this ID IQ I0 the grid reference current, and we sense the grid reference current, and we compare the of course to get the error, and have a PWM current controller for getting the signal for that. And the inverse transformation matrix of course aligned to the D axis like. So, these are the of course we discuss about 3 control algorithms which are normally very popularly used, but there are plenty of algorithms which we already given the classification and name of the algorithm. So, coming to now modeling and simulation of and performance of shunt active power filter. Well, taking for the modeling the data of the system 415 volt and 50 hertz system with the source impedance of resistance of 0.04 and inductance 1 millihenry and 3-phase rectifier with the R 2.5 ohm and L 25 millihenry, that is the nonlinear load we can say, and the cutoff frequency of the low pass filter DC low pass filter we take 10 hertz and the switching frequency of 10 kilohertz and sampling period of 10 microsecond. And these are the typically the performance of the 3-phase 3-wire active power filter for compensation of nonlinear load for harmonic elimination, and you can say these are the your nonlinear current of the load, and these are the supply current after the compensation, and these are the shunt active filter current. But here we do the load unbalancing also by removing the load on one phase, then becomes a load of line to line connected single phase load, and still it is you can call it a nonlinear or distorted current. So, of course, in this phase now you have a sinusoidal current, but other two phase will be the difference of this sine wave and this wave, and you will find that supply current are balanced, sinusoidal and unity power factor. And DC link voltage regulator, otherwise you cannot have a operation of D STATCOM like on. And these are of course you can see the TAD of the typically of the your load current, PCC voltage, and this is TAD of typically of the your load current, like they are both are sinusoidal, and this is TAD of course harmonic spectrum of your load current. So TAD from 23.65 it is reduced to less than 3% or so by using this shunt active filter. This is another case of course 4-wire system, modeling of 4-leg 3-phase 4-wire shunt active filter. So we have again supply data of 415 volt 50 hertz and source impedance 0.04 and 1 millihenry as a source inductance, and we are taking again 3 single phase rectifier because it is a 3-phase 4-wire system with a resistance of 2.5 ohm and L equal to 25 millihenry, and the DC link voltage again cutoff frequency is kept 10 hertz and the switching frequency of 10 kilohertz and 10 microsecond is the your sampling time, and these are the typically the performance at 3-phase 4-wire nonlinear load. So, you can see typically the 3 single phase nonlinear load, and that causes the load neutral current. You can see the sum of 3 is a neutral current here, okay, and but you can say the grid current is balanced sinusoidal and neutral current of the supply is also 0. These are the typically you can call it like a 3 current of the your shunt active filter, and the current for of course the 4th leg will be just opposite of that, and when we remove one phase load, so load remains still in 2 phase, so neutral current also changes corresponding to that, and your that phase current also now remains sinusoidal because supply current are sinusoidal. So, it provides like you can call it neutral current compensation, harmonic elimination as well as load balancing in this your typically at 3-phase 4-wire system like, and you can see the typically the voltage TAD it was 3.24 at the point of common coupling, but the current TAD is only source current TAD or supply current TAD is only 3.05%, it goes sine wave. However, the load current TAD of this load current of single phase it was like a 36.46 like. So, we are able to reduce from 36.46 to hardly to less than 3% or so, less than 5%, that is the standard like. So, coming to like a implementation of shunt active filter, many of our own like a group research student have implemented it in the laboratory, and these are the experimental result with this. So, these are the 3-phase source current as 3-phase typically the supply voltage with the 3-phase supply load current, and this is the power, you can call it the power typically of the active power source power there, and this is you can call it like a source current, but this is the load current. You can see the load current how it is non-linear, and this is the shunt active filter current. So, difference of typically you can call it difference the difference of this and this is this current. So, you can say sharp notches in the shunt active filter, and that is the reason we were saying that is indirect current control, and the grid current TAD is only 3.9% even when the voltage was reasonably distorted with the 6.4% TAD. And load current TAD was 26%. So, even voltage TAD was 6.4, but current TAD is 3.9. So, that is the reason which I mentioned earlier that voltage also we have to filter before using in the control like. And these are typically the load variation if one phase load is removed. So, you can say how the 3-phase supply current reduces here, and DC link voltage is regulated with slight overshoot for short period when load is removed. And you can see if this is the A phase grid current, then the load current of A phase and the shunt active filter A phase current. So, once load is removed, these two currents become equal. So, shunt filter current as well as the grid current become the typically you can call it because there is no load in that particular phase, but it is because of the load balancing you are just having this current in that. So, coming to typically again the implementation of 3-phase 4-wire system for neutral current compensation also. So, this is you can call it 3-phase grid current which are in phase with the voltage to sinusoidal balance current, and neutral current is almost 0, but you can see 3-phase current like square wave. These are kind of square wave, and this current is you can see the neutral current in the load. This is reasonable neutral current, and these are 3 shunt active filter current, and this is your neutral current in the 4th wire like typically like typically. So, well you can see the now the TAD of voltage is 1.8% and the current TAD 1.9% and the load current TAD 36.8% like also. So, and this is the dynamic performance. You have a 3-phase grid current and a 1-phase load is removed here, and this is the load current where 1 phase is load is removed, and here is the grid current of the DC link voltage grid current and the load current and the compensator current, or you can call it shunt active filter current. So, till load was there you will see how the current are nonlinear current, the difference of these two current are fed by the shunt active filter, but once load is removed these two current become the same for load balancing like. and this is the neutral current of the load, and this is the neutral current of the your shunt active filter, and this is the grid neutral current like. So, that is grid neutral current is made 0 by fourth leg of the shunt active filter of this 4 leg 4 wire system. So, this is typically the with the simulation experimental. Now, we will be talking about some of the numerical problems like. So, a single phase shunt active filter is employed for harmonic current compensation of a single phase 230 volt 50 hertz fed diode bridge converter drawing 15 ampere constant DC current. Calculate the current voltage and VA rating of the active power filter to provide harmonic compensation at unity power factor. Let the supply is stiff enough so that the distortion in voltage at the point of common coupling is negligible, and this is the you can call it the typical circuit. We have a non-linear load with diode rectifier with the RL load and constant current on this side, and this is the shunt filter in you can call it in the shunt with the load, and very purpose is the harmonic elimination. So, you can say supply voltage, supply current that is in phase, and this is the load current, and the difference of these two is generated by shunt active filter, where the voltage of DC link is regulated. This is the DC link voltage of the shunt active filter, and this is the load current like you can clearly see here. That is constant, that is the reason it is coming square wave. So, coming to numerical part of it, given that Vs equal to 230 volt, your frequency 50 hertz and DC link current is 15 ampere in the single phase diode bridge. So, supply RMS current and the DC link current is the same, that is 15 ampere, and fundamental current of the typically of you can call it in this AC current is 2 root 2 by pi into IDC, that is 0.9 IDC. So, it is a 13.5 ampere, and the current rating of shunt active filter we can calculate IF equal to IH, that is all harmonic. So, IS square minus IS1 under root of that. So, putting the value of both these we get 6.538, that is the shunt active filter current, and the voltage rating of shunt active filter is the same as the load. So, that is 230 volt, and the V rating of this shunt active filter VF IF will be 230 into the current of active filter 6.538. So, it comes 1.503 kVA. Coming to the typically second numerical problems, the shunt active power filter, the voltage source inverter with the AC series inductor and DC capacitor shown in the figure is used in parallel with the single phase supply of 230 volt 50 hertz feeding diode bridge rectifier, charging a battery of 180 volt and 10 ampere average current with a small current limiting resistor to reduce the harmonics in AC mains current and to almost maintain unity power factor. Calculate the value of current limiting resistor, the AC input current to diode rectifier, the voltage rating of shunt active power filter, the current rating of active power filter, V rating of active power filter, the value of DC bus voltage of active power filter, the value of AC inductor of active power filter, and the value of DC bus capacitor of active power filter. Consider the switching frequency of 10 kilohertz, and the DC bus voltage has to be controlled 5%, and the ripple current in inductor is to be 8%. So, this is typically you can call it the load now. It is a voltage load because after diode rectifier we are putting a battery which is charging from this AC source, and this is the shunt active filter. So, after making a model and total simulation, you can see supply current, supply voltage and supply current which is in phase and sinusoidal. So, it means unity power factor, and this is the load current. So, load you will be drawing the current by the load only when your supply the supply voltage is more than the battery voltage. So, only short duration, and this is your compensator current, your shunt filter current, the DC link voltage, and this is the current which is flowing typically in the DC link of the load that gets reflected on the AC supply current. So, this is certainly the highly non-linear like. So, coming to the solution part of it, given that voltage 230 volt and we have some 325.27, that is peak of 230 with frequency of 50 hertz, and load current is 12 ampere with your battery voltage which is charged at 180 volt and switching frequency 10 kilohertz, and the ripple typically the ripple current 8% and the ripple voltage is 5%. In single phase diode rectifier with RE load, we can calculate for the conduction period the alpha at which you start conducting from this relation. So, it is a 33.59 degree, and then the beta, that is 5 minus alpha 146.40, and the conduction angle, the difference of this, it is 112.81. Out of 180 degree it is conducting only for this period, and the current limiting resistor is here R. We can calculate from the current is given 12 ampere. So, putting the value here, we can find out how much is will be the resistance which is limiting the current in this circuit. So, that comes for 4.973, and the RMS current in diode rectifier is a RMS discontinuous current of AC main. By putting this resistance value and all the other data, we are able to get now from this the typically the AC RMS current, that is 16.687, and the active power down from AC mains is IS square RS in plus the battery power EIDC, that comes 3554.763 watt, and the fundamental RMS current from AC mains will be IS1 equal to P upon Vs. This again 3554.763 by the voltage 230, so it comes 15.412, and the RMS current limiting resistor here we already calculated 4.9 and from this relation, and RMS current in diode rectifier also we calculated typically from this relation, so it comes 16.687, and the voltage rating of shunt active filter is same as 230 volt connected in shunt with the load, and current rating of your active power filter will be the filter current, that is ID AC side current is square minus fundamental current, so this comes 6.397, and the rating VA rating of the shunt filter VFIF, so voltage multiplied the current, that is 6.397, so it comes like a 1471.389 VA, and the value of the DC bus the value of DC bus voltage VDC to that comes typically like your 406, so we can take 400 typically, I mean considering the modulation index 0.8 like, and the interfacing inductance of shunt active filter from this relation corresponding to ripple current, so we can just find out this comes 19.539, and the DC bus capacitance for active power filter is computed from change in stored energy from dynamic, and that is stored energy for typically single phase is only VFI delta T with this, and taking the value of minimum voltage of 380, nominal voltage 400, and that is from a filter side, so it comes 1886.295 microfarad. Coming to third numerical problem, a single phase shunt active power filter is employed for the harmonic currents and reactive power compensation for a single phase 230 volt 50 hertz fed thyristor fully controlled converter drawing a 10 ampere DC current operating at 30 degree fire angle of its thyristor. Calculate the current voltage and VA rating of the shunt active power filter to provide A. Only harmonics compensation, B. Only reactive power compensation, C. Harmonics and reactive power compensation at unity power factor. Let the supply is stiff enough so that the distortion in voltage at the moment of common coupling is negligible. So, this is the typical circuit. We have a load with the thyristor converter with RL load which have a 10 ampere on DC side, and we have a shunt active filter. So, after making the model and simulating with the proper actual data, so this is the supply voltage, supply current, load current, then the shunt active filter current, DC link voltage, and this is the DC side current which is given here like 10 ampere average like. So, coming to the solution part of the numerical data, given that source voltage is 220 volt 50 hertz and DC link current is 10 ampere and fire angle is 30 degree, and in single phase thyristor bridge converter, I mean because it is a square wave, so supply RMS will be same as DC link volt current, that is 10 ampere, fundamental will be 0.9 IDC, that is 9 ampere, and hence the total harmonic current will be your IS square minus IS1 square under root of that. So, putting value here it comes like 4.359 ampere, and the active power component of supply current will be your IS1 cos theta 1, that will be IS1 cos alpha, putting the value that 9 into cos 30 degree, that comes 7.794, and the total harmonics and reactive current will be IS1, I mean IF equal to IS1 square minus I1A, that is the only active component. So, keeping the value it comes 6.265 ampere. So, coming to only harmonic compensation, because we have to take in harmonic compensation, so current rating will be current flowing through the filter. So, that will be IF equal to IS, that will be IS square minus IS1 square. So, that is typically 4.359. So, this is only harmonics current in that, and voltage across this is the 227 the supply voltage, and the VA rating will be VFIF. So, putting the value it comes 959.98 VA, and only reactive power compensation. So, we can have this reactive current that will be IR IS1 sin theta 1, IS1 sin alpha, and 9 sin 30, that comes 4.5 ampere, and voltage rating is 220 volt, and VA rating is I mean typically 990 VA. So, harmonic current and reactive power compensation, the current rating of shunt active filter is IS1 minus S1 square. So, only active component is flowing into that, because you have to compensating harmonics as well as reactive current. So, this is comes like a 6.265, and the voltage rating is again connected in shunt. So, it is the same as the supply voltage 220 volt, and V rating will be typically your current multiplied the voltage, that will 78.30. This is higher than only which was for only for harmonic. This is for harmonics and reactive power also. Now, coming to the fourth numerical problem, resistive heating load of 20 ohm is fed from a single phase 230 volt RMS 50 hertz AC source through a phase control AC controller at a firing angle of 120 degree. Calculate the fundamental active power drawn by the load, fundamental reactive power drawn by the load, V rating of active shunt filter to provide only harmonic compensation, B only reactive power compensation, and third as a harmonics and reactive power compensation at unity power factor. Let the supply voltage is stiff enough so that the distortion in voltage at the point of common coupling is negligible. So, these are typical the load AC voltage control with the resistor. I mean, use plenty of application typically might be like you can think about like a heating elements, okay, or maybe I mean like lighting elements with the resistive load along with the thyristor controller. So, this is which draws not only harmonic, but it draws the reactive power, and you can see the load current pattern corresponding depending upon the firing angle, and this is the supply current at unity power factor after compensation, and this is your shunt active filter current, and this is DC link voltage, and this is your typically the current flowing into the load like. So, coming to the numerical portion of it, supply voltage is 230 volt 50 hertz and resistance of the load is given 20 ohm and firing angle of the AC voltage controller is 120 degree. So, in single phase control AC controller, the waveform of supply current has a value of Vs upon R and it conducts from typically corresponding to alpha to pi. So, taking the voltage to peak voltage of the supply will be 230 into root 2. So, that will be 325.27 and the RMS supply current will be your I mean from this stationary relation of AC voltage controller will be equal to 5.085 ampere, and the fundamental RMS current of course in the this resistive load with the AC controller I mean from this relation which is given most of the power electron is boosted. So, you can find out. So, from this relation, so it will come 3.549 and your let us say you can call it the angle between fundamental current and the voltage I mean from this relation in terms of alpha it comes 50.69 okay. And you can call it RMS active power component of the supply current will be IS1A equal to IS1 cos theta 1, that putting the value of both it comes 2.248 ampere, and hence the total harmonics current will be your IH equal to under root IS square minus the your fundamental current square, and putting the value it comes 3.642 ampere, and the RMS reactive power component of supply current will be IS1 R equal to IS1 sin theta 1, and putting the value of this, so it comes 2.746 ampere, and total harmonics and reactive current will be corresponding to IS square minus IS1 square. So, it comes 4.561 ampere, and the fundamental active power drawn by the load will be P1 equal to Vs IS1 cos theta 1, that comes 517.04 watt, and the fundamental reactive power drawn by the load will be Q1 Vs IS1 sin theta 1, it comes 631.58 VAR. So, the V rating of active filter to provide only harmonic compensation will be current rating equal to current flowing into the filter, that is IF equal to IH will be IS square minus IS1 square. So, putting the value it comes 3.641. So, this is the only harmonics current I mean, and the voltage rating across the filter same at 230 volt of supply voltage because it is connected in shunt, and putting the value of this VFIF 230 into 3.642, that is 792.26 VA, and if we want to have only a reactive power compensation, then the current rating of filter will be only reactive current. So, that will be IR equal to IS1 sin theta 1 and IS1 sin theta 1 I mean IS1 under root 1 cos theta square theta 1 square, that comes 2.746. This is only for reactive current compensation, and the voltage rating of course this shunt active filter is the same as the supply voltage, that is point of common coupling voltage 230 volt, and the VA rating is VFIF, that is the reactive power fundamental reactive power Vs1 IS1 sin theta 1, and it comes 631.58 VAR. Now, coming to harmonic current and reactive power compensation. Now, here I mean the what will be flowing in the supply, it is only active component of current. So, remaining have to be provided by shunt active filter. So, IF will be equal to IH that is under root IS square minus I1 IS1A square. So, putting the value into this it comes 4.561 ampere. So, this is with harmonics as well as reactive power component like, and voltage rating of the filter is the same as the supply voltage because it is connected in the shunt, and the VA rating will be your VFIF into the voltage and current 230 into 4.561, which we calculated here, and it comes your 1049.03 VA. So, it is compensating for not only harmonic, but reactive power also. That is the reason its rating is increased compared to other two cases like. So, coming to the fifth numerical problem, a 3-phase shunt active power filter is employed for harmonic current compensation for 3-phase 415 volt 50 hertz fed diode bridge converter drawing 100 ampere constant DC current. Calculate active power drawn by the load, current rating of active filter, voltage rating of active filter, the V rating of active filter to provide harmonic current compensation at unity power factor, value of DC bus capacitor, value of AC inductor, the value of DC bus capacitor of APF, and consider the switching frequency 10 kHz and DC bus voltage to be controlled within 5% and the ripple current is 8% like. So, this is the typical case that we have a supply, we have a shunt active filter, and this is the load, we have a diode rectifier with highly inductive load. So, you have on DC side constant current, but AC side it will be like a similar to like a Cauchy wave current. This is the supply current, and this is the current in all three phases of load current here which is flowing, and these are of course the shunt active filter current like common also. So, in this case, so coming to the numerical part of it, given that the voltage is equal to 415 by root 3, that is 239 by 9.6 volt and frequency 50 hertz, and your DC side current at your 100 ampere, and now the Cauchy square wave RMS current on the grid side will be IDC under root 2 by 3. So, it is 81.65 ampere, and moreover the RMS fundamental current will be also of Cauchy square wave will be IS1 under root 6 by pi into IDC, that becomes typically like a 77.97, and the active power drawn from by the load will be 3 Vs IS1 cos theta 1. So, it comes 56.045 kilowatt, and the current rating of active power filter is the total harmonic current, that is your IAPF equal to IF equal to IH under root IS square minus IS1 square, and that is 24.236 ampere, and the voltage rating of the filter will be voltage across the filter, that is 239.6 volt, and the V rating of shunt active filter will be 3 VFIF, that is 2 into 239.6 and current 24.236. So, it comes 17.421 kVA, and the value of DC link voltage will be from this relation will be corresponding to like a typically of 752 volt. So, it comes 750 volt, and the interfacing your inductance of the APF will be corresponding to ripple current from this relation. So, it comes 4.187, putting the value all value it comes 4.187 milli Henry like and the DC bus capacitance of active power filter is computed from the stored energy during the dynamics. So, change in stored energy during dynamics will be corresponding to this relation which we already discussed many times. So, we say that we allow the voltage little around 8% less. So, it says minimum voltage is this is nominal voltage, putting the value here of this energy with the recovery of energy within half a cycle. So, capacitance comes 6352.907 microfarad. Coming to like another numerical problem, a 3-phase shunt active power filter is employed for the reactive power compensation for a 3-phase 3-wire 415 volt 50 hertz system. A non-linear load consisting of 3-phase diode rectifier sorry is drawing AC current at 0.92 displacement factor, and TAD of its AC current is 60%. It is drawing 15 kilowatt from AC source and crest factor is 2.5 of AC current. Calculate the current voltage and VA rating of active power filter to provide A only harmonic current compensation, B only reactive power compensation, C harmonic current and reactive power compensation. So, this is the typical circuit. I mean you have a kind of voltage fed kind of load, after diode rectifier you have a capacitive filter with resistive load, and this is the shunt active filter which is connected in parallel to that. And these are you can see after making a model and putting the real data. So, this is the simulated performance. So, these are the 3-phase grid current and 3-phase supply current which are in after compensation which are in phase with the supply voltage, and these are of course 3-phase load current. You can see the 2 notches in the load current, I mean in this voltage fed kind of load, and these are the current of the shunt active filter, and this is the typical DC link voltage regulated, and this is the typically the current on the you can call it like into the here like I mean which are shown typically here like I mean. So, coming to the numerical part of it, given that the supply voltage per phase is 415 by root 3, that is line voltage by So, it comes 239.6 volt and frequency 50 Hz. Total harmonic distortion of the grid current is 60%, that is given, and displacement factor given 0.92 and crush factor is given 2.5 and active power of 15 kilowatt. So, in 3-phase diode bridge rectifier converter, the fundamental active power component of supply current is IS1A equal to P upon 3 Vs, that is 20.868 ampere, and the RMS fundamental supply current is your IS1 equal to IS1A divided by dPf. So, it comes like a 22.683 ampere, and the distortion factor from TAD we can calculate, it comes 0.857, and the power factor which is defined in this power electronics application, distortion factor multiply displacement factor. So, we have both here and it comes 0.789, and the moreover the RMS supply current is your IS equal to P upon 3 Vs into Pf, it comes 26.452 ampere. So, now coming for the calculation of voltage and volt ampere rating of the active power filter for only harmonic compensation. So, current rating will be the current rating flowing through the filter. So, that is IS equal to IS equal to under root IS square minus IS1 square. So, that comes like a putting the value of your, you can call it RMS current minus the fundamental current square. So, it comes 13.0608 ampere, and the voltage rating because it is connected at the PCC. So, voltage is the same as the voltage phase voltage 239.6 volt, and VA rating will be 3 times the phase voltage, and then phase current it comes 9.782 kVA like. And if you want only reactive power compensation, so current rating of filter will be reactive current, that is your IR equal to IS1, typically your reactive current equal to sin theta 1 and the IS1 under root 1 minus dPf. So, it comes 8.89 ampere, and the voltage because it is connected in shunt. So, it is the same as the PCC voltage, that is Vf equal to Vs, that is 239.6 volt, and V rating of active filter will be 3 Vf IF. So, putting the value like this is the your reactive current which have to be given by your shunt active filter. So, it comes 6.39 kVA like. If you want harmonic current and reactive power compensation both together, then we have to find out certainly the filter current from the active component of current. So, IS square minus IS1A square, putting the value of this, it comes like a 16.255 ampere, and the voltage rating of the typically the filter is the voltage across the filter. So, that is Vf equal to Vs equal to 239.6 volt, and the V rating of the filter will be 3 VIF, and putting the value of this, it comes 11.684 kVA like. So, coming to the numerical example 7, a 3-phase shunt active power filter is employed for harmonic currents and reactive power compensation for a 3-phase 415 volt 50 Hz fed thyristor bridge converter drawing a resistive load of 10 ampere at 30 degree fire angle of thyristor. Calculate the fundamental active power drawn, fundamental reactive power drawn, V rating of active filter to provide only harmonic current compensation, only reactive power compensation, and along with harmonic current and reactive power compensation at unity power factor. Let the supply is stiff enough so that the distortion in the voltage at the point of common coupling is negligible. So, this is the typical circuit, like we have a load here, thyristor converter with the R load, and we have a shunt active filter which is connected at the PCC, and after putting the value and making the model, these are the waveform 3-phase supply voltage, supply grid current which are in phase with the supply voltage. The case only one is taken here, that is providing all the components. These are the load current, these are the shunt active filter current, this is the DC link voltage regulated, and this is the DC current on the resistance side like. So, coming to numerical part of this solution, given that supply RMS voltage is 415 by root 3, that is 239.6, frequency 50 Hz, resistance 10 ohm and fire angle 30 degree. So, in 3-phase thyristor bridge converter, the waveform of AC supply current is decided by load resistance and fire angle edge. So, we can find out RMS current from this relation of typically in that case for resistive load, and it comes 40.286 ampere, and RMS of fundamental component of current for this comes like IS1, from this relation it comes like 37.966 ampere, and the hence the total RMS current harmonic current will be your IH equal to IS square minus IS1 square. So, it comes like a 13.472 ampere, and the active power once we know fundamental current. So, from this relation we can find out active power consumed by the resistive load, it comes on DC side 24.34387 kilowatt. and the active power component of supply current will be P upon 3 Vs. So, it comes 33.866 7 ampere, and displacement factor is cos theta 1. So, we can find out from your active component of current divided by RMS current. So, it comes 0.892, and sin theta 1 will be then under root 1 dpf square. So, it comes by 0.45197, and the total harmonics and reactive current will be your Is square minus Is 1 square, that is putting the value, it comes 21.8176 ampere, and fundamental active power drawn by the load P 1 will be equal to 3 Vs Is 1 cos theta 1. So, it comes your 24.34387 kilowatt, and fundamental reactive power drawn with 3 Vs Is 1 cos theta, it is 12.334 kVAr. And coming to like now rating of the your shunt active power filter only for harmonic compensation. So, current in the shunt filter will be If equal to IH under root Is square Is 1 square, only harmonics current. So, that will be putting a value is a 13.472 ampere, and voltage rating will be the same as the PCC voltage per phase, that is 239.46, and the VA rating will be your 3 Vf If, putting the value 3 into phase voltage phase current, it comes 9.68387 kVA, and only reactive power compensation. So, we have a current for reactive current is Is 1 sin theta 1. So, it comes 17.1597 ampere, and the voltage rating is the same as the PCC voltage, that is 239.6 per phase voltage, and the VA rating 3 Vf If. So, it comes 3 Vs Is 1 sin theta 1, it comes 12.33424 kVA, and if now the rating for harmonic current and reactive power compensation both we want to do it. So, that is If equal to Is square minus Is 1 square. So, putting the value of this, it comes 21.81, typically 8176 ampere, and voltage rating will be the same at the PCC voltage 239.6, and VA rating will be 3 Vf If, putting the value of this, it will be your 15.68261 kVA. So, this rating is certainly higher than this rating which is used for only for reactive power. So, here we are able to discriminate between all the three rating only with the harmonics, only with reactive power, and only harmonics and reactive power like. So, we stop here.